Because there are a few students who got very high scores, I don't feel that it's fair to set the maximum at the maximum score um, for the test. So what I propose is that we consider 100 points to be 100%. Then a few people will have got up to 106%. And some people will be in a lower range, most of them in the 80s and 90s, a few below that.
When will they be able to see their scores?
Um, let me make sure everything is graded. I can publish them now.
Oh, okay, so let's give everybody a minute to look at their scores. So how about if we do this? You can look at your scores, and I'll talk about for U.S. citizens how we need to, building on Farnham Jahanian's email, I'll talk about how we need to remain unified and not each other's enemies. Um, okay, so you go look at your scores.
Here, I still have to
Oh,
post them.
I just up. So there's a question about Monday's lecture on YouTube. I just uploaded it just before this class. So if you're a U.S. citizen, you may be feeling nervous now. Uh, I'm feeling nervous. The election shows how divided the country is. And if you notice that I seem shaky, it's because I keep thinking about 2 years ago when a white supremacist shot people that I know. And in a synagogue here in Pittsburgh. And the reason was that they were having a weekend program on to help immigrants. And the white supremacists wrote in a manifesto before the shooting that the Jews were a direct enemy because they were helping to bring immigrants to replace white people. Whatever side you're on is okay, but we can't continue thinking that we are each other's enemies like this. Somebody who perceived my people, another American who perceived my people as his enemy, shot people that I know. We have to stop this. Whatever the result of the election is, we have to come together again. We are not each other's enemies. Okay, so keep looking at your scores while I pull myself together for a minute.
I'm just posting them now. These are not normalized. So this will be the raw score. And I'll take care of the normalization later. So it should improve your grade. But this is your raw score, and you should be able to go in Canvas or in Gradescope and issue a regrade request. If you can view your exam and issue a regrade request if you're uncomfortable with how a particular problem was graded, and we'll do our best to get to those.
Okay. Okay, I'm going to give everybody a minute to look at their scores and ask questions about their test scores.
I have a question. So
Yeah.
are the scores correctly entered right now? Because I see a very low score for my grade.
I just checked them. They're correct.
Okay.
So David, since you're going to be traveling in the next day, what is the schedule for people to ask questions if they want to go over parts of the exam?
So I'll be able to do that starting Monday.
Ah, okay. I can try to answer questions by looking at the scoring rubric. If people want to get some idea for, since David graded all but one problem of the exam, he's the ultimate authority on your score. But between now and Monday, I can um, I can look at the scoring rubric, and so 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 David, can the students see the rubric that shows what they gained and
Y-
lost points for?
yes,
Okay.
yes.
Okay, so I'll do my best. If anyone has questions before Monday, you can contact me. Um, Kushal asked, do we know what the average highest is so we can get an idea of what the normalized scores will look like? So David, you just addressed that a few minutes ago.
Yeah. So just take your score and reinterpret it as a percentage.
And what is the lowest score?
The lowest score is 48.
And Tanmay asks, are question-wise scores uploaded on Gradescope?
Yes. So I've never done regrade requests in Gradescope before because I've never been a student. So I'm not sure exactly how the mechanics of it work, but I think you log into Gradescope and can go to the assignment and do it there. Um, oh,
Okay.
here I can send you a message.
I cannot see my grade on Gradescope, but I can see it on Canvas.
I just sent an email that should have the link. It should be possible now. Try again, or look at the email and click through, I think, a link there. To view your graded work.
Yes, that works. Thank you.
Okay.
Okay. So how about if I start on today's slides?
So I have some questions. Like
Go ahead. Yes, go ahead.
I have certain answers that are correctly mentioned, but I do see 0 points that are assigned for quite a lot of those answers.
So,
Um,
so you should make regrade requests for
okay,
those in Gradescope, and then we can go back over those and reevaluate them.
okay.
Okay. Does anybody else have questions? Okay. I'm going to start on today's slides. Um, slideshow. Okay, so today we're going to start a unit on syntactic formalisms. So what is a formalism? Formalisms are things like programming languages and regular expressions. They're languages that allow you to write some kind of code. Lexi and XFST are formalisms, so you have already used formalisms in this class. So in this part of the class, we will cover formalisms for syntax. So we have some ambitious learning goals for today. So on the left, I've extracted from the lecture notes. Words are grouped into units and they're arranged in hierarchical structures. Formal languages are able to represent an infinite set of sentences built from a finite vocabulary. Syntactic formalisms are like, in a syntactic formalism, you can write rules that become an accept-reject machine and provide a derivation for each sentence and also whether it's grammatical or ungrammatical. Now, on the right side of the screen, I've given more detail of what we're going to look at today as an overview. Finite state formalisms like Lexi and FST are not adequate to describe a kind of recursion, and we'll talk about what recursion is, a kind of recursion called center embedding. Context-free grammars are not adequate to describe a kind of structure called cross-serial dependencies. Context-free grammars are inconvenient when there's a proliferation of categories like singular count noun, plural count noun, singular mass noun, transitive verb with 3 singular subject, transitive verb with other subject. Okay, context-free grammars are rather inconvenient for that. Context-free grammars may not show, for example, that the students ate the chocolate is related in meaning to the chocolate was eaten by the students. Those two sentences have the same agent and patient. And because of this, linguists have invented other formalisms. So that's an outline of what we're going to talk about today. Oh, let me make sure I can see the chat. Okay. Okay, so this slide shows words that are grouped hierarchically into chunks called constituents. And the reason the constituents exist is to help construct the meaning of the sentence. So, so the sentence on the right may take you a little bit of time to interpret. In the sentence on the right, man is a verb. So to man the boats means to like staff the boats, to be the people who work on boats. The old man the boats. And on the left, we have the old man is sleeping. And we can see that in the hierarchical structures shown here, I realize I haven't told you yet what SDP, determiner, NP, and so on means. So we'll get to that. But if you just look at the way the groups are structured, you can see that in the sentence on the left, the old man is grouped together into one subtree. So a component of the meaning of the old man is sleeping is the old man. The meaning of the old man is sleeping includes the meaning of the old man. But on the right, the old man is not grouped together into a unit. And the meaning of the old man, the boats, does not include the old man is, an old man is not a component of the meaning of the sentence on the right. So any questions about that? Words are grouped into hierarchical structures and the pieces of the hierarchical structure are there to help you construct meaning. So each subtree is called a constituent, and we'll talk about constituents more on Monday. And the nodes of the trees are labeled with uppercase abbreviations, and these are called node labels. And if they're uppercase, they're called non-terminal symbols. So here's a list of abbreviations that were used in these trees. S for sentence, DP for determiner phrase. And you might be saying, if you have not taken other linguistics classes, you might be saying determiner phrase. Yeah, it turns out there's good reasons for that to exist in addition to a noun phrase. So determiner phrases are oriented around determiners like this, the, those, these, that. We talked about the part of speech determiner last time, and determiner phrases contain noun phrases. AP is an adjective phrase that would be like for the word old. And I pulled a tricky thing on you here. In sentence B, I said that old is a noun. DET is determiner, A is adjective, and is noun, and B is verb. Okay, any questions about this? So the nodes of trees are labeled with uppercase characters that are called non-terminal symbols. And the words at the bottom of the tree are called terminal symbols. So trees can be modeled with context-free rewrite rules. Can you raise your hands to tell me if you have ever encountered context-free rewrite rules? So raise your hand if you have, if you are familiar with context-free rules. You might have encountered them in a linguistics class or a programming language class or discrete math. Okay, so some people have not raised their hands. Okay, so we're gonna go over this. How to pronounce the rules. So there's something on the left, there's an arrow, and there's something on the left, and there's something on the right. So there are three ways. The bottom one, S goes to DP, NP, is the most common things that linguists say. You could say S rewrites as DP, VP, sorry, S expands to DP. I shouldn't say NP, that should say VP. Okay. Okay, I promise I'll fix this later. S expands to DPVP. Okay, so if you look at the tree, you can see that at the top of the tree is an S node, and that the S branches to a DP and then a VP. And the rules tell you that that's allowable. A DP can branch into a determiner and a noun phrase, and a noun phrase could branch into an adjective phrase and a noun phrase, or a noun phrase can just contain a noun. A verb phrase can expand into a verb, and here I have another verb phrase. So is a verb, and sleeping is another verb phrase, which consists of just a verb. Or a verb phrase can expand into a verb and a determiner phrase. And we previously saw that a determiner phrase can expand into a determiner and a noun phrase, and a noun phrase can be just a noun. So for the moment, is it clear how the rules correspond to the trees? Does anybody have a question about that? Okay, Sudesh says it's clear. Okay, so a context-free grammar is just one type of grammar formalism. And I've drawn some other pictures here of other grammar formalisms, and we're going to see why these were developed, why context-free grammars were not considered to be adequate for describing the grammar of human languages. So let's talk a little more about what a grammar formalism is for. So one thing that it does is it distinguishes strings. I realized as I looked over these slides that sometimes they say strings, which is maybe what you would call them in formal language theory, and sometimes they say sentences. Strings means sequences of letters or sequences of words. So when we're talking about formal language theory, we're talking about sequences of some kind of symbols, and we're talking about human languages, we're talking about sequences of words, and those are called strings of words. And strings of words can be phrases like noun phrase or verb phrase, or they can be sentences. So here's a sentence: the girl sees a boy. And if you look at the context-free rules, you'll remember that a sentence can break into a noun phrase, the girl, and a verb phrase, sees a boy. A noun phrase can further break down into a determiner, the, and a noun, girl. And a verb phrase can break down into a verb and another determiner phrase, which then breaks down into a determiner and a noun. So you can see that the sentence, the girl sees a boy, is consistent with the rules on the previous slide. But girl, the has a star on it. It's not an acceptable sentence or phrase or string in English. And you'll notice that the context-free rules on the previous slide have no way to describe this sentence. A sentence can start with a noun phrase. Oh no, it doesn't even start with a noun phrase. No, we can't even start this sentence because all of those rules required every sentence to start with a determiner, I think. Yeah, these rules only describe sentences that start with determiners. Obviously that's just a sort of sample set of rules. That's not like the real rules of English. And in fact, one thing that's important to know is that there is no set of correct rules. Everybody who writes grammar writes it in a different way. And every algorithm that learns a grammar by observing trees that were built by humans might learn it with different probabilities and weights. So there is no correct context-free grammar. Okay, but you can see, does everybody see that there's no way for the grammar to produce girl, da. And anything you try with those rules will fail on girl, da. It's just, okay, so the grammar describes a set of sentences that are allowable in the language. So the other thing that a grammar is good for is to get the structure into good pieces that help you get the meaning of the sentence. So using this grammar, we can get a nice structure for a girl sees a boy. And so it's in nice pieces that are relevant to the meaning. A girl is part of the meaning of a girl sees a boy. Sees a boy is part of the meaning of a girl sees a boy, and a boy is part of the meaning of a girl sees a boy. So we get really nice pieces of this sentence using this grammar. But if we wrote a different grammar, we could still, this grammar says a sentence starts with an NP, and now I'm using NP instead of determiner, determiner phrase. So again, I want to point out there's no correct grammar. And the purpose of these lectures on syntactic formalisms is not for you to learn a correct grammar. It's to learn how you use a formalism to write different grammars. And right, so it's to learn what kind of formalism is good and how you use the formalism to write different grammars. So this grammar says, okay, a noun phrase is a determiner, and a verb phrase can start with a noun and then a verb and then a determiner. So we see that here. The sentence starts with a noun phrase, it's just a determiner, and then there's a verb phrase that has a noun, a verb, and a determiner, and then there's another noun phrase. Oh, and then there's just a noun, a noun phrase, a verb phrase, and a noun. Okay. So in this tree, the girl is not a constituent. Remember, a constituent is a unit or complete subtree. So the girl is not a constituent in this tree. But girl sees a is a unit in this tree. And this tree is considered to be undesirable. So this grammar, because this grammar describes this tree, this grammar is considered to be undesirable. Any questions about that? Does anybody like this tree? Or think that maybe some unsupervised machine learning might come up with this tree and what's so bad about it? Okay, I'll take that to mean nobody wants to defend this tree. Okay, so now I'm going to talk about recursion. Recursion is a situation in a set of grammar rules or in a tree, well, let's say in a tree, where a non-terminal symbol x directly or indirectly contains another x. So x, so remember the most common way to read these arrows is goes to, and I'm really not sure how that happened, but that happened in the 1960s. People started pronouncing the arrow as goes to. X goes to y, x. So you can see that an x contains another x. And that would, or x goes to y, z, a y and a z, but then the z can be a w and an x. And you can see that, let's take x goes to y, x, you would just keep going around in circles. That x expands to y and x. Well, how does that x expand? Well, it expands to y and x. Well, how does that x expand? That one expands to y and x. Okay, so it's going to make long trees. So what is recursion for? I should say on the previous slide, in case you're wondering, in case you're worried that the derivation of the sentence would never end, you usually do add a termination for the recursion, which is just x goes to y. So you do allow it to stop at some point. Okay, so what is recursion for? Recursion allows a finite set of rules to describe an infinite set of sentences. So I put dots in here to show that you could keep going. The students, mothers, sisters, friends, teachers, book. There's not a clear point. There's a point at which if you keep adding more possessive nouns, the sentence is going to become extremely impractical. But there's no cutoff point where you can say, yeah, this just isn't grammatical anymore. And we'll talk about that more later, the difference between competence and performance. Practically, you don't want your noun phrases to get that long. But there's actually no deciding line where you could say, yeah, 5 possessors is okay, but not 6. Okay, any questions about that? About a finite set of rules describing an infinite set of sentences and how that happens. So that's what recursion is for. So now I want to talk about finite state grammars or regular grammars. So those are names for the same thing, compared to context-free grammars. So regular grammars and context-free grammars are 2 different formalisms. So regular grammars are a formalism and context-free grammars are a formalism. Context-free grammars are more flexible in the kinds of rules that they allow you to write. So what they have in common is that on the left side of the arrow, there is exactly one non-terminal symbol, like an S or an NP or something like that. Where they differ is what can be on the right side of the arrow. For a regular grammar, what can be on the right side of the arrow could be all non-terminal, all terminal symbols. The lowercase ones are the ones that don't expand any further. You can also have one non-terminal symbol in a finite state or regular grammar. But either all the rules that have non-terminal symbols have to always have the non-terminal last on the right, or all the rules, so all the recursion is going to be going to the right, or all the recursion is going to be going to the left. But you can't have both. In context-free rules, you can have any combination in any order of terminal and non-terminal symbols on the left-hand side of the arrow. So I know that there are some people who have not seen this before, and this is abstract, and we are going to, part of this lecture will be to show you concretely why finite state or regular grammars are not adequate for the syntax of human languages. And it's going to have to do with something called center embedding, where the recursion is in the middle, not strictly on the right or strictly on the left. For computer scientists, would you like to say anything that you know about regular grammars? Or is this okay? Okay, so so we saw two formalisms, and each one describes a class of languages. So in formal language theory, if you would take a class on formal language theory, what you learn about is what kind of language can be described by formalism. For example, regular or finite state formalisms allow grammars with recursion to the right and to the left, but not recursion in the middle. So you can talk about a type of formalism and what type of language the formalism can handle. And so for people who do programming, you know that you wouldn't be happy if all you could write were regular expressions. You wouldn't be able to program a lot. So a finite state grammar, which it is equivalent to the language of regular expressions. The class of languages described by a finite state grammar is the class of languages that can be described with a regular expression. And you wouldn't be real happy if that was all you could program with. But the other thing that's important about formalisms is how long it takes an algorithm to determine the structure for a sentence and to determine whether it's grammatical or ungrammatical. So I believe regular languages are linear and context-free grammars are generally polynomial. Any computer scientists want to say anything about that? Or we can go on. Okay. One of the things that Noam Chomsky did before, we mentioned before that he's a very famous guy. One of the things that he did in computer science at the very beginning of his career in the 1950s was that he defined something called the Chomsky hierarchy of formal languages. So context-sensitive languages are the ones that allow more than one symbol to the left of the arrow. And he showed that the class of languages that you can describe with a context-sensitive grammar properly contain the context-free languages, and the context-free languages properly contain the finite state or regular languages. So if you can describe something with a finite state machine, you can describe it with a context-free grammar, but not vice versa. So I know this probably sounds abstract to people that haven't done formal language theory yet, so I want to get more concrete here. Okay, so let's go back to looking at types of recursion. This is a right branching recursion. It's recursion because the S's contain S's and the VPs contain VPs. This is right recursive. All the branches off to the right. So you have S becoming an NP and a VP, and the NP doesn't branch, but the VP branches to the right. And then this S is an NP and a VP, and the VP branches to the right. And then this S is an NP and VP. So all the branching is to the right. And if you had a finite state machine, you could say, well, you have a start state, and then you can have the noun phrase like Jan. You'll see why I've used Dutch names in this sentence later. Jan, Piet, and Mary. I guess it should have been Marie. So you can go to a state where you've seen Jan, and now you're going to see a verb like saw, and then you're going to see another noun, Piet, and then you're going to see a verb, help, and then you're going to see another noun, Mary, and then you're going to see another verb, swim. So you can do this, but this finite state machine won't give you this structure. It won't tell you, there's nothing in this. It says, okay, noun, verb, noun, verb, noun, verb. That's fine. Just alternate nouns and verbs. But it's not going to tell you that saw Pete help Mary swim as a subtree, or Pete help Mary swim as a subtree, or Mary swim as a subtree. So any questions about that? The finite state machines can describe this sentence, but and as accurately as you have to alternate nouns and verbs, but it won't give you the structure. So it should be, yeah, on the finite state machine, it would be better if I had said noun and verb instead of noun phrase and verb phrase. Yes, thank you. I will change that before I post the slides. Any other questions about this? Okay, so so that was right branching, and I think I have an example of left branching. Here's an example of left branching, the student's friend's teacher's book. So you can see that book is on the right and the branching, and then we branch to the left. Student's friend, student's friend's teacher, book, the branching's on the left. And you can see that that's an example of left branching. But now we're going to look at a type of.
I have a question regarding that.
Yeah.
So which one is preferred? Or which one is correct, or which one is not correct, or
right or left branching?
yes.
You need both. So for possessive noun phrases, to get the constituents right, like if you think about the meaning of this noun phrase, the student's friend is part of the meaning of the student's friend's teacher. So this correctly groups the words with groups on the left. But here, for embedded verb phrases and embedded sentences, we need to know that it is raining is a component of the meaning of she will say that it is raining. And say that it is raining is a component of the meaning of will say that it is raining, or she will say that it is raining. So for these embedded verb phrases and sentences, right branching is a good structure. And for possessive noun phrases, left branching is a good structure.
I see. Thank you.
Yeah, we actually need both. Both structures occur in human languages. Okay, any other questions about that? Okay, so now I want to talk about a type of recursion called center embedding. And this is where the recursion is in the middle, not on the right or on the left. And then we're going to talk about whether human language has center embedding. Yeah, this is going to be maybe a little mind bending. Brace yourself. Okay, so here's a context-free grammar that shows the recursion in the middle. So A is a terminal symbol and B is a terminal symbol, and the recursion, the S containing another S, that's in the middle. And then we need a way to end the recursion so that we don't go on forever. Like an S is an A, an S, and a B. Well, what's that S? Well, that S is an A, an S, and a B. Well, what's that S? That S is an A, an S, and a B. And we need a way to stop. And so we finally stop by saying, when you're done, just put an A and B. In formal language theory, is an abstract reasoning about formal languages using A's and B's. But we'll see on the next few slides how this corresponds to real sentences in English. So abstractly, this is what we're talking about, but we'll see how this corresponds to real sentences. One kind of way that it might correspond to real sentences is here. If S, then S. Oh, so let me show you here. The important thing, this language is called A to the N, B to the N, because every tree it builds has the same numbers of A's and B's. So, and you can see why that's true, because of this recursive rule. Every time it adds an A, it adds a B. And then finally, in the end, you add one A and one B to end the recursion. But one A and one B, and then you recurse again, one A and one B, and then you recurse again. So it keeps the A's and B's locked together so that every time you have an A, there's a corresponding B. So it's A to the N, B to the N, where N is the same. And that's how formal language theory describes the language that you get from this grammar. It's a grammar with center embedding recursion in the middle, and it's a language where the number of A's is always the same as the number of B's. So let's look at some things in English. Like we need the number of ifs to be the same as the number of thens, or the number of eithers to be the same as the number of ors. So that's a situation in English where it's like needing the same number of A's and B's in a kind of center embedding. But this isn't the example I'm going to focus on. I want to show here that this is why we call it center embedding or nested dependencies. Because if you consider which A and which B are produced in the same application of the same rule, this A and this B are produced in the final application of the rule S goes to AB. But this A and this B are produced in the same application of the rule S goes to ASB. And this A and this B are produced in the same application of the rule. So what we say is that the A's and B's are paired with each other. And you can see that the pairing of A's and B's is nested. This A and B are inside this A and B, and that's inside this A and B, and that's inside this A and B. And that's sort of the same here with if either S or S, then if S, then S. This either or is nested inside of that if then. Okay, so now let's look at a different type of center embedded sentence to ask ourselves, does English really have center embedded or nested dependencies? And let's think about this sentence. The windows the man you recommended washed are clean. I think I need to hear from people about whether you can understand that sentence. Let me see what I have on the next slide. Okay, so you can understand. Okay, so can you understand this sentence? We're going to break it down. Does anyone want to complain about it? The windows the man you recommended washed are clean. So notice that, yes, it is kind of hard to understand. So you could say the man you recommended washed the windows. So, okay, but I want to point out something about this. And there's going to be a breakdown of this sentence coming in a few slides. The number of noun phrases matches the number of verb phrases. So this is in A to the N, B to the N. And yes, this should be hard to understand. So don't worry if it's hard to understand. We're gonna break it down into smaller pieces. So people would use this sentence with the same number of noun phrases and verb phrases to show that English does have an A to the N, B to the N type of structure. Noun phrase, noun phrase, noun phrase, verb phrase, verb phrase, verb phrase. And you can see that even in the tool I used to draw these sentences, they even automatically got numbered right. Noun phrase 1, the windows are clean. Noun phrase, verb phrase 2, the man washed. And noun phrase 3, oh no, it's not right. No, sorry, the numbers aren't right. So you recommended, the man washed. Yeah, the sentence SI plus 1 is matching the NP. NPI. No, it's more like sentence 1. Yeah, actually, the numbers are actually not relevant. They're an artifact of the tool I used to make the tree. And you'll see later that I didn't use this tool anymore. So the windows goes with clean. The windows are clean. The man is the one who did the washing, and you recommended. So you can see that the nouns are paired with the verbs and that there's the same number of noun phrases and verb phrases. Okay. Okay, can someone remind me to come back to this slide of why finite state machines can't do this? I'll get back to this one later. Okay, do human languages have A to the N, B to the N? So let's look at the structure a little more closely. So let's look at what a relative clause is, because that's what's going on in these sentences. Relative clauses are sentences that modify nouns. So we have the noun, the man, and then that you recommended is a relative clause. And one thing about relative clauses in English is that the word that at the beginning of the relative clause is optional. So you can say the man that you recommended, or you can say the man you recommended. So you can say the windows that the man washed, or the windows the man washed. Okay, so the relative clause is the sentence you recommended or the man washed. Any questions about that?
Here are some results.
Oh, Google thought I was talking to it. Okay, any questions about that? Maybe remind me after we finish talking. Sidesh says, sure, when do we remind you? When we finish talking about center embedding. Okay, So let's start with the windows. And we add a relative clause to windows, the windows that the man washed. Now we want to add a relative clause to man, the windows that the man, not just the windows that the man washed, but the windows that the man that you recommended washed. Okay, so we're embedding relative clauses inside of relative clauses. And there's going to be a picture here. Yes. Okay, so let's see how this happens. The windows are clean. But now we're going to put another relative clause after windows. The man washed. We're going to add that after windows. The windows the man washed are clean. Okay, so that's good, right? Everybody can understand that one. And it does have this A to the N, B to the N property. 2 noun phrases, 2 verb phrases. But now suppose we want to add another relative clause after man. The relative clause is you recommended. So now we have the windows the man you recommended washed are clean. Starting to get harder to understand. Some people said they could understand this one, that the windows the man you recommended washed are clean, but some people said it was hard to understand. But you can track on the right here that we're kind of just doing an A to the N, B to the N thing. We start with AB, the windows are clean. We add another AB, the man washed. And then inside of that, we add another AB, you recommended. So we're doing an A to the N, B to the N. Thank you. So the number of noun phrases has to be the same as the number of verb phrases. So the windows are clean, that's good. The windows the man washed are clean, that's good. The windows the man you recommended washed are clean. A little hard to understand, but still pretty good. But the windows the man are clean, that's not good. 2 noun phrases, 1 verb phrase. The windows recommended washed are clean. That's bad. 1 noun phrase, 3 verb phrases. That's no good. Okay, so we need the same number of noun phrases and verb phrases. So now I'm going to come to the questionable part that causes people to disagree. All of the sentences on this page have the same structure, exactly the same structure as the windows the man you recommended washed are clean. So oysters eat is like the windows are clean. Oysters eat is like the windows the man washed are clean. And oysters eat. Oh God. Okay, so the trick is you have to say this with the same intonation as the windows the man you recommended. Oysters. The windows the man you recommended washed are clean. Oysters eat. Now that is incomprehensible, right? I need to see that you agree. Can somebody tell me that you agree? Yuan says, what? Okay. Are you asking agree with what? Or agree that oysters eat is incomprehensible? Do you agree that oysters eat is incomprehensible? Yes, Yuan agrees that it's incomprehensible. But can you understand oysters eat? Yeah, that one makes sense. Sidesh says that one makes sense. So let's look at the one in the middle. The rat ate the cheese. The cat ate the cheese. That's good, right? You can understand the rat, the cat ate the cheese. Okay, but now when we get to 3 noun phrases and 3 verb phrases, the rat the cat the dog chased bit ate the cheese. It's like, no way. No, like, no way. You cannot understand that. Oddly, it has the same structure as the windows the man you recommended washed are clean. And then to get truly ridiculous, since to buffalo somebody can be a verb, and buffaloes can buffalo buffaloes, buffalo nouns can buffalo other buffaloes. If buffalo is a verb, then you can get the truly ridiculous structure. Buffalo, okay, I'm not even going to say it. So this is like a party game. As a party game, you can practice saying these sentences with the same intonation as the windows the man you recommended washed are clean. But this raises a question. If the bottom sentences here with 3 nouns and 3 verb phrases are so incomprehensible, does English really have A to the N, B to the N? Okay, so first I want to show you that just to, for people that have taken linguistics, you might have realized that the trees I was showing you were not how linguists really build the trees. And this is the real way that linguists write these trees. And I showed the trees the other way just for the purpose of exposition to the computer scientists. So they could see the similarity to the A to the N, B to the N grammar. So any question about this from the linguists? This is what the trees should really look like. Okay. Okay. So there's a problem. We have seen AB, 1 noun and 1 verb phrase. That's good. We've seen 2 nouns and 2 verb phrases. That's good. But we've only seen 1 example of 3 nouns and 3 verb phrases that we could understand. And most of the time we can't understand 3 nouns and 3 verb phrases. So do we want to say that English has this, that English has A to the N, B to the N, or that English doesn't have A to the N, B to the N? And the other issue is that if center embedding, recursion in the middle, is so limited, in fact, it can be done by a finite state machine. You just have to write a lot of states, but you can do it. So if center embedding is really limited to really 2, A to the 2, B to the 2, does this really show that English is not finite state? Does anyone want to have an opinion about that? What do you think? Does English really have A to the N, B to the N? Salvador, is that yes for does English have A to the N, B to the N, or is that a yes that was left over from before?
It was a leftover from the meaning of the sentences,
Oh,
if
the
we
meaning
could
of the
comprehend them. Yes.
Okay, so nobody has a strong opinion about whether English really has A to the N, B to the N. Okay, so let's, okay, I think, okay, so just to show you that A to the 4, B to the 4 would just be totally ridiculous. I'm not even going to try to say it. Oh, maybe I will. The windows the man, the woman you met recommended washed or cleaned. It's like suddenly this is like complete failure. This is just like absolute failure. So 4 is really bad. So what would Noam Chomsky say? Well, Noam Chomsky says there's a difference. Noam Chomsky would say, yes, English has A to the N, B to the N. But there's a difference between competence and performance. And we're going to see maybe today, depending on what time it is, we might see today that it just shows that your memory, people in computer science will know what a stack is. It's just like we've got a really short stack. But Noam Chomsky says, yeah, your competence, your knowledge of the rules of English tell you that this is a possible structure. And the fact that you can't process it, it just shows that you have a short stack. So he says English, you have a short memory. Like you can't remember all these noun phrases in order. By the time you find the verbs that you have to match up in the same order, it's like your memory's gone. So he says, yeah, we have A to the N, B to the N. It's just a practical matter, a processing matter. So he distinguishes competence, which is, yeah, English has A to the N, B to the N, from performance, which is your performance is affected by the size of your memory. Okay, so that's what Noam Chomsky says. We don't have to agree with him or not agree with him. Does anybody have a feeling about this? Okay. But, okay, so now let's look at something that can't, oh, okay, so this is where I have to go back to finite state machines. And I might need help from people that have taken formal language theory to explain this to the people that haven't. A finite state machine can make sentences with the same number of nouns as verbs. It doesn't have any trouble doing that. It's that it can't it just makes them in a loop. So there's no way to trace as this tree is expanded. There's no way to trace that each A goes with each B. So it can't produce this structure. But worse yet, there's no way to force the same number of A's to be the same number of B's. So finite state machines can make all these sentences, but they also make the bad ones. Finite state machines can't make only the good ones. Do you want, okay, so people could ask questions about that. Take my word for it. You might already be convinced because you can see that in order to keep the A's and B's together, you need recursion in the middle and maybe you understand that finite state machines by definition, just by definition, don't allow recursion in the middle. So anyone want to comment on that? Okay. So it turns out that there's something even worse that happens in natural language. And I think David has gone off to prepare for traveling. But David's wife speaks a language that has what's on this slide, which is called a cross-serial dependency. And so instead of a nested structure, we have a cross structure here. So this occurs in two languages that I know of. This one is Dutch, and the other is Swiss German, which is where David is heading right now, to where they speak Swiss German. That's where his wife is from. And so David's wife speaks a language that does this. We, a child, the old lady, the street, let, help, cross. So let goes with we, child goes with help, and the old lady goes with cross. And then the street is the object of cross. So there's actually 3 subjects and 3 verbs, and the street is an object of a verb. So this means that we let the child help the old lady cross the street. Near the bottom of the screen, you can see nested dependencies is what we saw before for A to the N, B to the N. But what we see here in this sentence with the first A1 going to B1, the first A going with the first B, in a nested dependency, the first A goes with the last B. So this is something that cannot even be handled with context-free grammars. I'll just move on and leave this here for you to think about that. Whether this is the fact that two Germanic languages are known to have cross dependencies, which context-free grammars cannot do. I'll just let you ponder what that means. But there are a lot of papers written about this. Okay, so what is beyond context-free grammar? And why would we need to go beyond context-free grammar? So the first reason would be a lot of the work on grammar formalisms is done by people who speak Dutch. They're really big into grammar formalisms, and they're not going to let us get away with leaving them out. They've got cross-serial dependencies. Not all dialects of Dutch. It might be a dialect of West Frisian. Okay, but they're not going to let us get away with leaving out the cross-serial dependencies. So what are some other things that people were not happy with context-free grammar that led them to try to develop more complex grammar formalisms? So another one is that in the 1950s, linguists were thinking about what sentences mean. And Noam Chomsky's advisor, Zelig Harris, thought about kernel sentences like the students ate chocolate or a dog bit the man. And then he thought, you know, we really want to group sentences together when they have the same semantic roles. So the students is the agent of the students ate chocolate, and chocolate is the patient. And when you say chocolate was eaten by the students, the words are in a different order, but chocolate is still the patient of eating, and students is still the agent of eating. We talked about these role names, agent and patient, last time, just to remind you. Or a dog bit the man has a dog as the agent and the man as the patient. And the man was bitten by the dog. Also, the dog is the agent. The dog is the one doing the biting, and the man is the patient, the one getting bitten. So what Zelig Harris and then Noam Chomsky started thinking about was, yeah, we don't want these to be just have different rules. They're going to come from completely different rules. We want them to be related in some way. And maybe even sentences like it was chocolate that the students ate should be related to the students ate chocolate. Or what did the students eat should be related to the students ate chocolate. They shouldn't all just be, the purpose of grammar shouldn't just be to spit out grammatical sentences, but we should be able to know when the semantic roles are the same. And this is what's really important. For people that are studying syntactic theory, for linguistics majors who are studying syntactic theory, the purpose of syntactic theory is not to make the trees. It's not just to make the trees. The purpose of syntactic theory is to associate each noun with a semantic role like agent or patient. In natural language processing, parsing and semantic role assignment are two different tasks. And I think I mentioned last time that parsing is much easier than semantic role assignment. Syntacticians in syntactic theory do the two together. And the purpose of syntactic theory is to get the right semantic roles on the right nouns and also in the right structure. Okay, so what did Noam Chomsky do when he wanted these sentences to be related? He invented, or maybe, well, I'm not going to claim that he was the first person to think of a deep structure, but he made it popular. That you have a set of context-free rules that makes basic sentences, like the kids ate the chocolate. And then, but those context-free rules don't make all the sentences. So that's part of the formalism, is the context-free rules that make some structures, and we call those deep structures. And in the deep structure, this is important. The agent is always in the same place. The agent is always where the subject goes, and the patient is always where the object goes. Even though we know that in the surface, the chocolate was eaten by the kids, the chocolate is not the agent. In the deep structure, the agent and patient are always in the same place. So if you give two sentences the same deep structure, they're going to have the same semantic roles. So Noam Chomsky popularized something called a transformation, which was a meaning-preserving tree-to-tree mapping. Now, it has to be meaning-preserving because you can't just switch. You can't, like, here's an example of something that's not meaning-preserving. Turning the kids ate the chocolate into the chocolate ate the kids. That's not meaning-preserving. They don't mean the same thing. But turning the kids ate the chocolate into the chocolate was eaten by the kids, that is meaning-preserving. So transformations are, so transformational grammar had two types of formalisms. One type of formalism was a context-free grammar, and the other type of formalism was a meaning-preserving tree-to-tree mapping. So the context-free grammar makes the kids ate the chocolate, but not the chocolate was eaten by the kids. And then the meaning-preserving tree-to-tree mapping makes the chocolate was eaten by the kids. So that was an example of a grammar formalism that goes beyond context-free. And I think I said these things. Syntactic Structures was a book that Chomsky wrote in 1957. And I'm not going to go over this auxiliary verb thing right now, but I'll just leave it there if, in case people are curious. This is what really nailed it for people. This treatment of English auxiliary verbs converted a lot of people to being followers of Noam Chomsky. And it was really history making. It really changed the field of linguistics completely for the next 50 years. So now I'm just going to give you a kind of a preview of, a note to end on, a kind of a preview of where we're going to go next time. A limitation of context-free grammars is that they kind of get crazy when you have a lot of categories. So if you, okay, so we can say a dog sleeps and the dog sleeps, but not a dog's sleep or dog sleeps, or, okay, dog's sleep is okay. So the nouns have to agree with the verbs, and the singular count nouns, we talked about that last time. The singular count nouns need determiners. So dog isn't good by itself. You have to say a dog or the dog. So there's singular and plural, there's count and mass, and there's nouns and verbs, and the verbs agree with third person plural. So if you were really going to write a context-free grammar that doesn't allow the ungrammatical sentences, it would look like this.
I have a doubt on the previous slide.
Yeah.
So here, why, like, so the dog spreads the information versus the dog sleeps the information. So what is the difference between the two? And like, yeah, I understand that the second sentence is correct, but from just these rules, how can one say that?
From these rules, oh, okay. So the point is that the rules on the left are not correctly describing the sentences on the right. The rules on the left allow all the sentences on the right to be generated.
So yeah, so how can one generate this? The dog spreads the information from.
Oh.
Like, what is the difference
Okay.
between
Oh,
the
yes.
last two?
Need
Why?
another, there would
How?
have to. Yeah, sorry. I would need one more rule. VP goes to VNP. So sorry, I didn't write. Okay, so that's a third thing that I have to remember to update in these slides.
Okay.
Yes. Yes, thanks for pointing that out. Okay, so to get all of this right, and you can check to see whether I've really gotten it right, you would have to say, well, singular noun phrases, well, okay, so first of all, I didn't have transitive verb phrases in this grammar, but sleeps is an intransitive verb, so it can't have an object. So we want to get the dog sleeps, but we don't want the dog sleeps the information. So we want to say that a transitive verb has a noun phrase, and an intransitive verb just so here I've separated VP goes to V for intransitive verb and VP goes to V NP for transitive verb. And I have singular nouns and plural nouns and singular mass nouns. If it's a noun phrase that consists of only a noun and no determiner, that can only be a singular mass noun. So I had intended, and I don't know if it works completely, I had intended this grammar to correctly distinguish the grammatical from ungrammatical sentences on this slide. But you can see that we have a proliferation of categories. The thing on the left is called the lexicon, and it's a list of all the words. And the words, instead of just being determiner, they're now determiner singular count, or determiner singular mass, or determiner plural count, or determiner plural count, determiner plural mass. So the parts of speech are more complicated. The non-terminal symbols are more complicated. So we just have a big proliferation of categories. And this just becomes hard to manage. So this was one of the main reasons why people developed more complex formalisms. The formalism itself is more complex, but it allows you to say these things more concisely. So by making the formalism more complex, we can say complicated things more concisely. So that's what we're going to start looking at on Monday. Any questions before we go? Okay, then I will see you on Monday.
Professor, can we, is it possible to have a 2-minute discussion about the midterm?
Yeah, sure. Oh, when will homework 4 be due? I'm sorry, I still need to reschedule. So all of the quizzes and homeworks had to be rescheduled because the midterm being a take home and taking a week instead of a day put us completely off schedule. And I apologize, I haven't rescheduled everything yet. But homework 4 has not been announced, and quiz 3 or 4, whichever we're up to, or 5, has not been announced. I will reschedule all those things, I promise. Okay. All right, so I'll stay on for people to ask questions. Let me see, hang on. Okay. And I'll stop recording.